So we have section 11.2, vectors. You've just read through and reviewed the topics from pre-calc, so we're going to hit the highlights and talk about them very quickly. So we need to remember a vector is an entity that has both magnitude and direction. And an example would be something like what? What can we represent as a vector? Very often we take velocity and we come up with a velocity vector. Okay? A scalar has magnitude only. Scalar, for our purposes, are just numbers. Okay? Just values. No direction tied to them. Notation. We need to be clear that vectors are written in many different ways. And in our book, you'll see a vector notated with an arrow above a letter, vector A. You'll see it also written as what looks like a point but with pointed brackets. Okay? And you also will see it as an x-coordinate times what's called I hat plus a y-coordinate next to j hat. I hat and j hat are the unit vectors in the x direction and the y direction. So basically it says I'm going x units in the x direction and y units in the y direction. Okay? You should have read in the book also that the unit vector is called the direction vector. It just helps you realize which way we're going. Okay. All right. A little review of vector mathematics. Oh, also, in our text, they also use a bolded lowercase letter to represent a vector also. All right? So we need to be able to identify. So read the problem carefully so that you make sure you're picking up that we're talking about vectors. All right, so if I have something like vector u is 1, 2, and vector v is negative 5, 2, if I want to add them, add the x's, add the y's. Easy enough. So we have 1 plus negative 5 and 2 plus 2, giving us 4. If we are doing subtraction, then we can just subtract the way that we normally do, but it's helpful when we think about the graphical representation of subtraction that we take one vector plus the negative of the other vector. Okay? And as you see up at the top, over here, if I have this is vector u, then negative u, the negative u vector is the same vector but going the opposite direction. Okay? Scalar, as I said, was just a number. So if I am multiplying a scalar by a vector, then we just distribute the scalar through the vector. So we have 6 times vector 1, 2 would be the vector 6, 12. Okay? Any questions on this? All right. So sometimes we are asked to add vectors graphically, and there are 2 methods. The first method is called the tail-to-head method. So you would put your first vector here. There's our u. And then to add v to that, we put the tail of v at the head of u. And the resultant then goes from the origin to the end of the combination of the 2 vectors. Okay? The second method is the parallelogram method, where both of your vectors are drawn from the origin. So here's our u, here's our v. We translate a copy of u over to here, making it parallel, and we translate a copy of v up to here. The resultant goes from corner to corner. Notice that both of those, u plus v's, are the exact same vector, just done 2 different ways. All right, and this is where I said when we're doing subtraction, it's kind of nice, because if we were doing u minus v, we would do u here, and then we would do the negative v vector would come this way for our subtraction, or we could put it down here. Okay? Now, important for today is that any vector that we have, so my green arrow represents my vector, and any vector that we are given we can break up into 2 components. Right? I can make 2 other vectors, in this case a horizontal vector and a vertical vector, that would get me to the same location, as my result. And we need to remember from right triangle trig, if I'm looking for the horizontal component, it's the length of my vector times cosine 28, and the vertical component would be the length of my vector times sine of 28, and that's just using SOHCAHTOA. Okay? All right. The direction angle. Little reminder here that if I have a vector, I can always use right triangle trig to find the angle theta. Most often, I will use tan to get there because that uses a horizontal and a vertical. So we can use tan inverse of y over x to get our angle. Okay? All right. Now, let's look at the new information. The vector v over, what do the two bars around v represent? Magnitude of v. It's a vector of magnitude 1 called the unit vector. Its component form is cosine theta comma sine theta. And its direction, where theta is the direction angle, and that's why sometimes it's called the direction vector. All right, so now for the calculus, it's identical to what we did earlier in the year. All of the relationships hold. We just have to work with two components instead of one. So, position vector. When we deal with vectors, most often we are modeling motion of something. Particle of motion, and what is the velocity, what is the acceleration, where does it end up. Vectors are very helpful with that type of problem. So, we often start with a position vector, most often written as r, and it has an x component and a y component. It could be a function, or it could just be values, 1, 3. Could be cosine t, sine t. Okay? Well, how do I get from position to velocity? What do? We take a derivative. So we take dx dt to get our x component of velocity, and dy dt to get our y component of velocity. Speed is the magnitude of velocity. And we need to remember speed is a scalar. There is no direction when we talk about speed. Acceleration then would be the derivative of velocity with respect to t for the x component and the y component. And as we stated above, the particle's direction of motion is the direction vector, which is the unit vector that we get here. All right, and then we have displacement and distance. So suppose we have a velocity vector that has an x component that is v1 of t and a y component that is v2 of t. To get our displacement will still be a vector. So we just need to integrate from a to b our x component and our y component. And then to get the total distance traveled from t equals a to t equals b, we would integrate the magnitude. So here is your reminder, which I thought I had somewhere else, but we'll add it here. Simply to get the magnitude of, let's say, vector v, where vector v is v sub 1 of t, comma v sub 2 of t. And we want the magnitude what over x? Am I going the wrong way? Oh, of natural log, no, it's x log x minus, it's x minus x log x. Yeah. All right, so if I want the magnitude of that vector at time t, then it is simply the square root of v1 of t squared plus v2 of t squared. Anytime that we want to find the magnitude of any vector, its length. The magnitude is just the length of the vector. Think about the hypotenuse or the distance formula that we use to get the length. That's all we're doing here. Okay? Now, what I want to do is use all of this information to apply it to the lab activity. Your homework for tonight is on your assignment sheet. It's the first assignment for 11-2. Very straightforward. Should not take a lot of time. The problems that you'll be doing in the lab are definitely more involved. All right, so I want to start with those and work with those together. All right, so take out your lab and let's start looking at that.